1845, Gustav Kirchhoff came up with two laws involving electric circuits. They turned out to not be laws themselves, so now we call them Kirchhoff's rules, okay? The first one is called the loop rule. And what the loop rule says is that if you have any loop of electrical current flow, the total voltage has to add up to 0. And if you think about it, that should make good sense. This spot has a particular voltage. When you come around, when you get back to that spot, it still has to have that voltage. So something like a battery can add voltage, resistors and things will subtract voltage, but as you go around the loop, you end up with a total voltage of 0. So that means that in a simple, say, series circuit, the total resistance of all of the resistors has to decrease the voltage as it goes in order to end up with the voltage of the battery. The total voltage drops across the whole thing is equal to the voltage given by the battery. Now, that loop rule is not a law because it's actually an expression of something else. Once you know that voltage is energy per charge, what we're saying is that the energy given to an electron has to equal the energy taken away from the electron by the time it gets back to the same state. This is really just conservation of energy. Applying this to a series circuit, batteries are where electrons gain energy. When they hit the first resistor, they lose some of their energy. When they hit the second resistor, they lose more of their energy. When they hit the third resistor, they lose the rest of their energy and are now at 0. Then the battery gives them more energy again, and the process repeats. And because voltage is energy per charge, that means that the voltage of the battery is equal to the sum of the voltage drops across each of the resistors. Regents, this is on your reference tables. AP, you've just got to memorize it. In this parallel circuit, let's look at the first loop. The battery gives the electrons voltage, and then they expend that voltage, they use up their energy, in the resistor. The potential drop across the resistor is equal to the potential given by the battery. But the exact same thing happens in the second loop, and in the third. Each branch of the circuit behaves as if the other two aren't there. Let's back up a second and look at this another way. The top half of this circuit is only one piece of metal, and same with the bottom half. So assuming we've got perfect wires, if I attach a voltmeter to say here and here, I'm going to get a particular value. But if I attach it here instead, that value is not going to change. The voltage difference between the top and the bottom part of the circuit is still the same. And that means all of these voltmeters will read the exact same value, which you can see on the Regents reference tables. Kirchhoff's second rule is, I think, even easier to understand than his first. It's called the junction rule. And what it says is anytime you have a junction of wires, so you have multiple wires that come in and leave, the total current going into the junction has to equal the total current going out. And like the loop rule, this is based on a conservation law. In this case, conservation of charge. The total amount of charge has to stay the same. And so current in equals current out of any junction. Let's take a look at that in a little more detail. In a series circuit, it's not even a junction per se. Any current that goes in one side of a resistor has to come out the other side, and then it goes into the next one and comes out the other side, and so forth. And this is reflected on the Regents reference tables with I equals I1 equals I2 equals I3 equals ... Remember how in parallel each branch acts like the other branches aren't there? So each branch carries its own current, but these currents start to add up in the wires that connect the branches. This branch has to carry both the green and the blue current. See if you can spot my typo there, and so does this one. While the main lines out of the battery have to carry all of the current, reflected on the Regents reference tables here. So it should be obvious at this point that if the total current coming into this junction is IT, and I1 goes this way, then the current going this way has to be IT minus I1. You can apply this same math at any other junction in the circuit. And there you have it, Kirchhoff's rules in English and in math. We're going to use these a lot when it comes to combined circuits that use both series and parallel elements.